Hello. In this video for MAC2233 Calculus for Business and Social Sciences, we'll be looking in Chapter 5, Section 5.3, talking about the second derivative and analyzing graphs. So we know that the first derivative is the rate of change, and we've seen it as velocity in some examples. So the question is, what is the second derivative and what does it tell us? So if t is time in hours and the position of the car at time t is given by the function s of t equals t cubed plus 2t squared miles. So the original, if you plug in the time in hours, it will tell you how many miles have gone. Well, if I take the first derivative, that would be velocity. And the first derivative would be 3t squared plus 4t. That would tell me the miles per hour, the velocity, the rate of change. What is it? Miles per hour. And in its acceleration, if I take the second derivative, so the second derivative of the original, or the first derivative of the first derivative, which is the second derivative, would be acceleration. That would be 6t plus 4 miles per hour squared. Miles per hour squared. That is how the car is accelerating, how the rate of change is changing. So here's an example. According to the laws of physics, an object near the surface of the Earth falling in a vacuum from an initial resting position under the influence of gravity will travel a distance of approximately s of t equals 16t squared feet in t seconds. Find the acceleration. So here's the original, which will tell us the feet. So if we drop something, this will tell us how many feet it's traveled in t seconds. Well, the original tells us feet. S of t equals 16t squared. If I take the first derivative, which is velocity, we get 32t feet per second. That's the rate of change. First derivative. If I take the second derivative, which is the first derivative of velocity, we get acceleration, which is 32 feet per second squared. Now you may be wondering, where's the variable? Well, it's because it's constant. When something is in free fall, its acceleration is constant at 32 feet per second squared. Now, we can check all this on the calculator a couple of different ways. One, if we go to the calculator, go to y equals, the original is 16x squared. The first derivative is 32x, and the second derivative is just 32. When I go to the table, and we have to set up the table by hitting second window, make sure it says Ask Auto, and then go to second graph for the table. If I plug in 0, if I'm dropping something, let's say down a hole, it's gone 0 feet and it's traveling 0 feet per second, but the acceleration in y3 is 32 feet per second squared. So 1 second later, the book is now 16 feet away, traveling 32 feet per second, and then how is the rate of change going to change? It's going to accelerate another 32 feet per second squared. So when I type in 2 seconds, now the book is 64 feet away, traveling 64 feet per second. Now again, that rate of change increased. What told me how the rate of change is changing? Acceleration. 32 plus 32 is 64. So if I do 3 seconds now, the book is now 144 feet away, traveling 96 feet per second. And again, we knew it was going to increase, the rate of change was going to increase because of the acceleration. We can also check all this in the calculator. If you remember these numbers, in the calculator, go to y equals. I'm going to get rid of y2, get rid of y3. We can check the first derivative and second derivative in the calculator by doing vars, yvars, function y1. We're going to refer back to y1 and we're going to refer back to y2. So let's go back to y equals. I'm going to hit math, scroll down to number 8, which is n derivative, and we're going to take the derivative of y1. So like we just did, vars to the right for yvars, number 1 for function, y1, comma, x, comma, x. And we learned that in a previous section. Then for second derivative, we're going to do math, number 8, But instead of doing y1, we're going to do like we practiced, vars, yvars, function, but y2, comma, x, comma, x. This is a way to check what we just did. Hit second graph or table, and it's the same numbers. So it's a nice way to check your work in the calculator. Okay, so let's do another example. For the first 15 months after the introduction of a new video game, the total number of units sold can be modeled by the curve S of t equals 20e raised to the 0.4 t, where t is time in months since the game was introduced. So the output is total sales, and the input is time in months. So if I want to know total sales at 10 months, I plug 10 into the original. So I can go to my calculator, go to y equals, clear what I have in there, y1, y2, clear, clear. In y1, I'm going to put 20, second ln for e raised to the 0.4x, close parenthesis. Go to the table feature by hitting second graph, delete what I have in there, push 10, and at 10 months, we have 1,092 games sold. So at 10 months, we've sold 1,092 games. Now the next question says, what is the rate of change after 10 months? So that means we're going to take the first derivative. So if you remember from derivatives, how to take a derivative in e, the number in front stays in front. Rewrite it, e to the 0.4t, times the derivative of the exponent. Derivative of the exponent is 0.4. 20 times 0.4 is 8. So we have our first derivative would be, which is velocity rate of change, 8e to the 0.4t. And if I plug in 10, we get 437. So we can check that in the calculator. Go to y equals. I'm going to put the first derivative in y2, 8 second e to the 0.4x. And I'm going to check it because in y3, I'm going to do math, 8 vars, yvars, function, y1, comma, x, close parenthesis. Now y2 and y3 should be the same. y2 is doing it by hand, y3 is checking in the calculator. So when I go to the table, notice that y2 and y3 can round off to 437 games. Good way to check your work. So I could say after 10 months, the rate of change of sales is increasing 437 games per month. Now if I want to know how the rate of, how it's accelerating, that would be second derivative. So we take the derivative of the first derivative. So the 8 stays in front. We rewrite e to the 0.4t. The derivative of 0.4t is 0.4. 8 times 0.4 is 3.2. E to the 0.4t. There's your acceleration function. If we plug in 10, we should get 175. So again, let's go to the calculator, and we're going to check it. So I go to y equals. I'm going to go to y4. I'm going to put in 3.2 second ln for e, 0.4x, close parenthesis. And then I can check this by saying math, 8 vars, yvars, function, the derivative of y2, which is our first derivative, comma, x, close parenthesis. Now y4 and y5 should be the same. So when I go to second graph, y2 and y3 were the first derivative, y4 and y5 are the second derivative, and they match, which means they did it correctly. We get 175. So after 10 months, the sales are accelerating at 175 games per month squared. So what is this telling us? Well, at 10 months I analyze, and I've sold 1,092 games. The first derivative is going to tell me next month, the following month, my 1,092 is going to increase about 437. Remember, it's increasing at all time, so this is just kind of like an estimate of what will happen next month, 437 games per month. Now, will I be selling 437 games every single month forever? No, that rate of change is changing to say that next month I'll sell 437, but after that, your rate of change is going to change by increasing another 175 games per month squared. So what this means is right now I've sold 1,092. I expect to sell another 437 the following month, but that's going to increase 175 more. So right now my game is very popular. I need to keep producing that game. Okay, and the next video, we'll check what happens at 30 months. Well, actually, let's go ahead and do it now. So what happens at 30 months? Well, the equation's different. We have 100,000 minus 20e to the 17.0.4t. And what happens at 30 months? So I'm going to go to my calculator. I'm going to go to y equals. I'm going to get rid of y1, get rid of y2. I'll leave y3, and I'll leave y5 because we'll use that to check. But in y1, I'm going to put 100,000 minus 20 second e raised to the 17 minus 0.4x, and then we're going to take the first derivative. So first of all, when I plug in 10, go to the table, plug in 10, make sure I type that in correctly, go to y equals 100,000 minus 20 e raised to the 17 minus 0.4t, perfect, and then I'm going to plug in 30 this time. After 30 months, we've sold 97,032 games. So after 30 months, we've sold 97,031 games. Now to find the rate of change, the derivative of 100,000 is 0. The negative 20 stays in front. Rewrite e to the 17 minus 0.4t. The derivative of the exponent, derivative of 17 is 0. Derivative of negative 0.4t is negative 0.4. Negative 0.4 times negative 20 is 8. E to the 17 minus 0.4t. And let's find out how are things changing after 30 months. So plug in 30. So I go to my calculator, go to y equals, in y2, I'm going to put 8, second ln for e, raised to the 17 minus 0.4x, close parenthesis. Remember y2 and y3 should be the same. Go to the table, 1,087, 1,087. So after 30 months, the rate of change is 1,187 games per month, which means I've sold 97,000 games. I'm expecting to sell another 1,187 games the following month. But will that stay the same forever? Well, we find the acceleration. So the derivative of the derivative. So the derivative of 8e to the 17 minus 0.4t, leave the 8, rewrite it, e to the 17 minus 0.4t times the derivative of that is negative 0.4. 8 times 0.4 is negative 3.2. E to the 17 minus 0.4t. We plug in 30. So I go to y equals. In y4, I plug in negative, make sure you use negative 3.2. Second e, 17 minus 0.4x, close parenthesis. Now y4, and y5 should be the same at negative 475, so we know we did it correctly. What does that mean? That means the following month we're expecting to sell 1,187 games, but then after that it's a negative, which means we're going to start losing. Our game is becoming not popular. So it looks like I should keep producing because I'm getting 1,187 more games, but the second derivative is telling me, wait a minute, be careful because this rate of change is going down. And we can check that, and that's why I like using the calculator. If I type in 31, notice the rate of change decreases. Rate of change decreasing. What's telling us that that rate of change is going to decrease? What's telling us how the rate of change changes? That's the second derivative, which is telling you, hey, slow down. Okay? And then we'll work on some other examples in the next video.